so today we need to talk about this. We need to find the average atomic mass zone. So you've got a short note here that says Introduction to Fractional Abundance, and we're going to do 2 examples. And the first example isn't going to have any chemistry in it at all. We're going to deal with just grades. Now, this class doesn't exactly break down this way, but a lot of classes at Rockhurst have a percentage grade. So let's assume you're in a class that has a grade with like 45% of it is tests, and 20% is homework, and 20% is quiz, and your remainder is a lab. That problem we need to write up on the board, but I don't have a marker, I dropped it, so I guess we'll do this again. Man, you'd think that would be able to draw better lines, but whatever, you have an example of it in your notes. This doesn't need to be perfect. I want you to see the process, even if my lines are a little squiggly. All right, so this question says a particular student scores a 72% in the test category. Ouch, but okay. Let's see, how's he doing on the homework? 95%, nicely done. Saving his butt. Quizzes, let's see, 85 and an 82 in lab. Okay, this is just going to be our weights later on, but this is a score. Now, what we need to do is apply a weight to the average. In this average, our tests matter much more than the other ones, right? We know that our weight for the test was 45%, right? Now we got to turn that to a decimal. 45% is not a decimal. All we're going to do is we're just going to move that decimal 2 times, boink, boink. So we have 0.45 instead of 45%. All right, so the next one, we said that our homework was worth 20%. So would that be the decimal? Hopefully you got that one right. Obviously this is also 0.2, and this is going to be 0.15. It's very important when you're doing this problem that this whole column must add up to 100%. Let's say must add up to 1. So 45, 65, 85, 90, 100. This works out well. If these numbers don't all add up to 1, aren't all 100%, the math isn't going to work. This is where I see students make the mistake. Now, what I want you to do is along the top of your page, pause this for a moment and write down something. That something is to multiply across, then add down. Our process in this is going to be doing a times operation for each row, and then at the end we'll have a column where we add down. It's really important. We're going to use this several times where we multiply across, add down. The reason why we're doing it in this order is it's going to help us out later on in chemistry when we do more advanced problems. So let's go back to our table for a second. All right, so we're going to multiply across and then add down. So each one of these rows exists independently of the column. Our math here is going to be like 72 times 0.45. The calculator is not 72 times 45, it's 72 times 0.45. Okay, the next one down is going to be 95 times 0.2, 85 times 0.2, 82 times 0.15, right? This is just a math problem where this number is being multiplied by this number. So it's obviously very important that we get these decimals right, otherwise we get the wrong weight. But it's pretty easy. So let's do that math really quick. All right, so we've done that math. We took this number times that number, we got this number. Now, the smart ones in the room are like, Mr. Nemec, that's 2 sig figs, and that's 2 sig figs, and that's 3 sig figs. You're right. So for sig fig reasons, I'm going to round it to the right number. If you didn't do this, I'm not going to be too picky about things, but let's face it, it's just a decimal. So what we're going to do next is we're going to take these numbers, and we're going to take 32 plus 19 plus 17 plus 12, right? We're going to just take this, and we're going to add down. All right, so we get 80, right? So this kid scores, based on this weighting structure, is an 80%. Now that's a bit contrived in example. What I really want you to see though is that multiply across, add down thing. Now, realistically, you're not going to calculate grades in this class. You're going to calculate chemicals. Let's look at what this would actually look like for a real chemical problem. Let's work one together, just one. All right, so we're looking at 2 isotopes of chlorine, chlorine 35 and chlorine 37. The first thing we need to do is set up a table. Our first column is just going to be the name of the chemical, its symbol, like this. Since we have 2 different chemicals, we need 2 different rows. If we have 5 different isotopes, we need 5 rows. Every new isotope gets a new row. The next thing we need to do is put in the weight or the AMU. I don't care which way you go. I'm going to take the weight. So I have 75.78% chlorine 35 and the other one 24.22%. So that would go in a new column like this. And I'm really careful to make sure that the atomic mass weight for the chlorine, the percentage abundance of it, the fractional abundance, use its fancy word, is matched the right thing. Like chlorine 35 is 75.78, not 24. Make sure that they go with the right one. Now, this is wrong. Why? And so what we need to do is, again, move those decimals twice. 0.7578, 0.2422. We can't just leave them as whole numbers. So let's clean this up. Of course, we're not done yet. We need something to multiply this by. So we need their mass number, right? Really, we need the weight of a chlorine 35 atom, of a 37 atom. And that will be given to you. You can't calculate this. You can't look it up on a periodic table. So it will always be given you to the problem. In this case, it says that 37 chlorine has an atomic mass of 36.966. It says that the 35 chlorine is 34.969. So we need to put those in and with the right column. So let me do that really fast. So we get something like this. And we need again to multiply these across. So this number times that number equals this number. This number times that number equals this number. Let's do that really fast. So we get this number. Round to the right number, sig figs, 4 sig figs, all these. So each of these have 4 sig figs. Because we now have addition, right? We multiply it across, we're adding down. We're going to use whatever our fewest number of decimals are. So our answer is going to have 2 decimal values. We can still add these together, which we'll do really fast. So I add them. I get this number, right? We got to round it to the right number of decimal points, which we've done there. 2 decimals, 2 decimals. And this problem is perfect. I want to see a grid like this set up when you do these problems. I don't want you just to do the math aside. I want you actually to physically write the grid out like this. It's going to help you later on, I promise. The only way I would take off points if you show me all this work is because you forgot your label. And for now, our label is going to be AMU. Now, there's a better unit for that, but not yet. For now, AMU. For this next test, AMU. Okay? Now, we have 2 things to do before I let you free to work on this. 1, I need to do just a couple quick, simple questions to make sure you've got what you need to do here, right? And then I need to talk for like literally 5 minutes about a couple concepts we haven't talked about in like states of matter and phase changes. Super fast, super easy, no big deal. Now, before we get there, let me clean up this board and get something to do for these questions. All right, let's say there's an awesome element called nendikium. And I tell you that there are 4 stable isotopes. Right off the bat, you know you need to put how many rows in your table. All right, good. Now, what we need to do is, let's say I know something about nendikium here, and I know its fractional abundance. I know its percentage of each one. They look something like this. Neat. Let's express this 18.4% as a decimal for me really fast. And what we're at, how about this 8.8%? All right, be careful. A single digit percent will be led by a 0. A decimal percent will be led by 2 zeros, right? Let's say you have something stupid like 0.51%. But that's still a percentage. You still need to move that decimal twice. Be careful. By far, the most common mistake in this is not converting your percentages to your decimals correctly. If you struggle with this, literally just type in the number from the percentage and divide it by 100%, per 100. Do that math. Be careful. The hardest part of this problem is setting it up. Now, we're not perfect on it yet. We need some practice on it. You're going to get some practice today when you work on it, and we'll work on this a little bit more when we come back from break. For now, let's talk about the states that matter for like 5 minutes more, and the rest of this class, all you have to do is work through this problem. If you can answer, keep posted, but work through these problems and make sure you've got it down. All right, so here we are looking at the states of matter. Remember that we left off talking about the phase changes of things. That is, the changes between one state of matter to another. And we said there are different kinds of it: deposition, sublimation, melting, freezing. We saw them in the lab. We saw the iodine go from a solid to a gas. So going directly from a solid to a gas, what would that be called? We also made some plasma, right? And a plasma is just a gas that's stripped from its electrons, right? The gas nuclei and the gas electrons are in different places. They're no longer a cohesive state of matter. You kind of get the soup of electrons and the nuclei differently. And so when you go from a gas to a plasma, what would you call that? And so this is important for us to have down and memorize. And I'll share these slides with you, but it should be pretty self-explanatory. What's less explanatory is that there's a spot when you can take away all of the energy, right? We said that as a solid, you kind of have shimmying, and a liquid, the vibration is so strong that the solid breaks apart, and the gas, as you break apart the liquid, the forces between the atoms are weak, or too weak to overcome the shaking, and then you add enough energy, and all of a sudden you've split the electrons away from the gas. We can go the other way. You can take energy away from something and make it colder and colder and moving less and less. And even a solid, you can make it so cold that it stops moving. And it turns out if you stop everything moving, you always hit the same spot, negative 273 centigrade, or absolute zero, which we're going to call 0 Kelvin, much more important to me. These are hard limits. It is impossible to go colder than absolute zero. If it is colder than negative 273 C, if it's colder than 0 K, it can't happen. So which of the following can't happen? I mean, technically, the coldest place on Earth is actually the coldest place in the universe. This lab succeeds in basically cooling things all the way down to absolute zero, or technically ever so slightly beyond it, but don't worry about that. And that's really cool that we can force things to stop moving. Now, that being said, all I need you to know is that we can't exceed absolute zero. But there's no absolute hot. You can keep adding energy to a system. You can always make it more and more hot, at least to this class. There might be something way inconceivably hot. There might be a spot, but for this class, any temperature that I ask is fair game. It's always you just can't get colder than absolute zero, right? There's no upper bound for this class. We can get temperatures like in the hundreds of millions into the trillions of degrees on Earth, right? This is the Z machine in Sandia, where we basically use a big pulse of energy to collapse things and try to ignite them in fusion. It's super, super important that we study high temperature, high pressure situations like this, because they may be helpful for energy production in the long run. But it's not like absolute zero where there's a thing stopping us from heating something up just a little bit more. We can always heat something up more. Now, believe it or not, that's all we have to talk about. We already know what matter is. We already said that you come from stars. We already said that everything basically comes from stars following the Big Bang. So that's about what we need. Let's go back over to the lab. I'm reachable by email if you need me to. Otherwise, have a great fall break, and I look forward to seeing you when we get back.